All right, we're going to start. So if you would like to take your seat, we're going to have a great last session of the day. I'm Kostas Bellaris. I welcome you all to this last session of the day. Long day, but you're still here. And you're going to enjoy a program on indoor air quality, comfort, and health. I have the pleasure of introducing our first speaker, Professor Livio Mazzarella from Politecnico di Milano, from Italia, and he's going to start, get us going on health-based IAQ design, a comparison among different approaches. Professor?
Thank you a lot. Thank you a lot for your presentation. First of all, I had to thank the organizer to be here. It's a very interesting conference, and I will try now to switch a bit on the problem of health, because sometimes we speak only about comfort and then we forget that it's better than comfort is the health. And I was involved with other friends during the COVID-19 pandemic, working on a tool to try to give the possibility to engineers to improve the HVAC system to avoid the spread of infection. And this is something which is going ahead in this direction. Now, how the professionals are going to design a ventilation system, I will call now ventilation system, then I will try to clarify, because ventilation system sometimes doesn't mean anything. Now, what we do, normally we have two ways, what we call the prescriptive approach and what we call the performance approach. In the prescriptive approach, which is the most used, we just have tables with the air change rates, for instance, and we say, well, we assume that if we have such air change rate, everything will be fine. Then we have instead the performance approach, which is going to estimate the indoor air quality through the pollutant concentration estimation. That means I'm going to check if my system is able to maintain the level of pollutant below a certain value. What's the problem? That in the prescriptive approach, the threshold are just the air change rate, very simple. We have certain change rate per hour and so on. The performance approach, the threshold are the pollutant. But the main problem is that several times when you are going to design the ventilation system, air conditioning system, full air or primary air plus other equipment, you don't know exactly what there will be there. You don't know what could be the pollutant. How you can design if you don't know what would be the load? Then if you know it, then it's an easy formula to calculate what should be the clean air, I would say, better flow rate to dilute the pollutant to keep below the concentration which is considered to be the limit concentration. Now, how we design today, we have several standards. We have the ANSI standard was mentioned before, the 62.1, ventilation acceptable indoor air quality. We have the EN 16798 part 1. I will skip all to go saying that we have there also the different method to calculate the flow rate, and the ISO 17772 part 1, which is just the same. One is SEN, the other one is ISO, but are identical. And then there is also the Israel standard 10001, which include threshold for indoor environmental quality, and then specifically also for indoor air quality. Now, how they works? The ASHRAE and the EN, the ISO and the ISHRAE, they use for the prescriptive approach the same, let's say, formula, same kind of approach. That means that binomial formula. Then we have two terms, one just for the airflow we need to provide for one person, then we have 10 person, we multiply for 10, and a part which is related instead for the release of pollutant by the building envelope and so on. Then one parameter is related to the number of people in the environment, the other one is related to the building typology. Then you have tables where you have the two values, QP and QB. And of course, as always, I said I prefer to speak about clean air because ventilation assumes that you have clean air outside, which is not always the case. Then it would be better to speak about clean air, then it's much clearer. Now, you can see what kind of table you have. This is for the 16790 and for the ISO. No, in this case, you have different categories you don't have in the ASHRAE standard. And then you have the flow rate per person per second and liter per person per second. And then you have different values for different categories for low polluting, very low polluting building, no low polluting building, no, according how much is released of pollutant from the building. Now, of course, you can have also a health-based prescriptive approach, because what we have done when there was COVID-19, we have followed the common approach, which was I fix a certain flow rate, and then I will see what would be the probability to get infected. Okay? But this is not a way useful for designers that like to know if I fix instead the probability, what would be the flow rate? And this would be the result at the end. But the prescriptive approach was followed by ASHRAE with the ASHRAE standard 241. You have a table there, okay? And also an ongoing review of EN 16798, part 1, part 3, because we'll be split it in 5 parts according to the 4 pillars of indoor environmental quality, thermal comfort, indoor air quality, lighting, and acoustic comfort. And there is now method 4 designed for airborne transmission. Both these methods will be prescriptive. Now, this is the ASHRAE standard 241. It's very simple to use. It's the minimum equivalent air flow rate. You calculate just from a table and number of people in the space. Then you have a table where you keep the flow rate you have to provide for 1 person. And then if you have 10 person, 10, 20 person, just multiply 4. Now, you see there the table, no? And I made a very simple example just to compare a different approach. If you have an educational facility, lecture hall, the tablet value would be 25 liters per second per person. Then if you have 20 person, we come up to 500 liters per second. This is the flow rate we need at minimum, no, to be on the safety side. Now, this is the proposal for the EN standard, the revision for the design for airborne transmission. And here we have a bit different formula where we have 2 terms again. One related to the airflow per person, n-1 is n person in the environment. One, the hypothesis behind is the infectious people, person. And then you have another term which takes in consideration what? The fact that you can have different removal mechanisms inside the space, and then you need less clean flow rate due to the fact that the virus is dying, there is deposition on the floor, and so on. But anyhow, you can go to see, again, there is a table here, few numbers, classroom, the example as before. Then, in this case, we have the volume. Then assume that the volume is 150 cubic meter. Then you see that I'm coming up with 154. Very different number. What's the best? We will see at the end. Now, common drawback of this approach, the prescriptive approach, that both methods don't specify what kind of virus I'm speaking about. No mention at all. Are all viruses the same? No, we will see later. What kind of activity level there is there, taking into account both for the infection and susceptible person. If I'm just breathing or speaking or loudly speaking, the emission will be completely different and the probability of infection will be different, and so on. Now, you can see we have completely different result. Then this was the reason to try to start to have an infection probability in long-range transmission. Okay, this is something very important to clarify. That means we are to have a simple tool, fast to give an answer. You cannot rely on CFD calculation, trying to give how the flow is going through the room from infection to susceptible person and so on. And then you have full mix hypothesis behind. That means that the result has some meaning only if we are talking, I'm talking here, you're sitting there. If you are nearby me, forget it. You cannot apply this. That should be very clear. We are talking about long-range transmission. Then you can use the full mix hypothesis. Then you can calculate in steady state the pollutant concentration or not in steady state in easy way, okay? Because you have average volume value. But I will not go really deeply. There's a lot of slides with a lot of math. I will try to simplify, to go direct to the concept and to the result. Eventually, we can come back later if you have questions, and we can go deeply in the basic behind. Just 2 slides with some formula. Normally, what you have is the pollutant is pulmonary virus. The steady-state concentration in quanta, these new terms, quanta, is related to the medical field, where they consider the result of infection in such unit, which is dimensionless unit, the quanta of infection. But then what is important is that what are the 2 elements? No, the concentration of, we can look at virus concentration to simplify, no? The virus concentration is related to what is produced and what we are able to take away with the removal effect of clean air, ventilation, okay? And then it's the ratio over there. If you know, usually from the medical field, the individual infection risk probability is a Poisson equation. It's so-called Rayleigh model if you consider steady state condition. And it's given, you see there, E by S. That means people get infected on the total of people can be infected. And it's an exponential, 1 minus an exponential decay, no? Where you have this DQ. This is the inhaled dose by a susceptible person, which depends on what? Depends on the concentration of the virus in the air and on your breathing rate. If you breathe a lot, you can get more, and then you have more risk. I mean, this is the basic of the old theory used by several researchers during COVID-19 and so on. Now, this was the steady-state approach and the Rayleigh's model, and this the inhaled dose by susceptible person. If you solve respect to the unknown, in our case, the flow rate, lambda is dimensionless total decay times the volume, you can come up in the last formula to the volumetric flow rate you need, okay, to maintain a certain probability, no, in the denominator, the logarithm. If you see now, this formula look like what we have seen for the new standard, the EN, no? There is one term which depends on the number of people, I, capital I there, and another term which is proportional to the volume, which depends on the natural decay, no? Because the virus is dying or there is some other, there is the deposition due to gravity when it's traveling through the air, okay? This is the Rayleigh's model, which is based on steady-state approach. What does it mean? When I start the calculation, immediately I'm in the worst condition, which is not the truth. Then you can step forward using instead the Gamma-Intoni and Nucci model, which is just taking consideration simple equation from who is able to manage, let's say, energy balance or mass balance in this case, where you take into account that you have a starting and then the people are coming in, also the infectious person, and then the concentration at the beginning was 0, and then it's growing up during the time. And then the formula you see is similar, but now you have an extra term, which takes in consideration the transient. Okay? Of course, if you stay 10 hours, maybe you reach the steady state. Okay? But if you stay 1 hour, the steady state approach will be too conservative. Okay? This is the first point, and then you have to use this. But. This is very straightforward. But the problem is that the models rely on what? Rely on the emission in terms of quanta, where we take this number, this value, from epidemiological studies from doctors in medicine. And do you know how many, let's say, samples they have? Maybe they have 10, 20. Maximum, they had 30 samples. That means the statistic is very poor and the dispersion is very high. Then the dispersion you can have on your result can be very high. And then you can have a very large range of uncertainties. Then, but just I will tell you the story without going inside. What we do here, we analyze the problem from the stochastic point of view. We assume that we can treat, because of this large dispersion, stochastically, and then there is a Monte Carlo simulation behind. And then I will skip 4 slides. If you're interested, we go in. Okay? And then you see here there is some discussion how we can go to reduce. And then we come up to the tool we have built. Forget about the number, are very small, but look the bar. Look the bar, the column on the right. I will explain the differences. Now, you have different colors. Input data, you can put everything you need. That means number of people inside the space, number of infectious occupants, the activity of the infectious person, if it's breathing or standing or walk, susceptible occupancy activity, because it's changing the breathing rate, okay? And the event reproduction number. This is the most, say, point of discussion. What we have to use? The probability, what we have to use? The probability of single person infection or the event infection reproduction number. I prefer the second, but anyhow, a lot of people prefer to use the first, but they are strictly related. Then on the green box, you can see the value. In this case, the value is 1.25, if I'm read well. What does mean event reproduction number? Means that if it's 1, I'm just reproducing the infection. Less than 1, I'm reducing the spread of infection. Greater than 1, I'm increasing the spread of infection. But then you can choose the exposition time. That means how long the people stay in the room, 1 hour, 2 hours, 3 hours, 5 hours. And then you use the transient approach to calculate what you need. Pathogen type, you can have a selection of different viruses. Here you see SARS-CoV-2, and RE is equal to 1. And then I have a personal infection probability, which is 5.3. Sorry, I was reading the wrong one. Exposition time, 5. Average quanta emission, 2.7. Equivalent quanta emission, 20.1. But what is interesting is the comparison. Then you have the EN standard we discussed before. Then we have the ASHRAE, 62.1. Then we have the proposal of the health-based ventilation for the EN. Then we have the ASHRAE 241, control of infection aerosol. And then we have the Italian standard, forget the last one. The color are related to. The green is just the calculation according to the model we have been showing before, okay? According to all the details you see there. The pink one is related to the EN standard, where we put the highest flow rate, first class, first category, and not low polluting building. That means a lot of release of pollution, then highest flow rate you can have. Then the purple one or violet one, it's the CO2-based calculation. In the standard, you have also threshold for CO2 according to the class, and then here we perform the calculation according, and the threshold is, if I remember memory, it's 550 ppm over the outdoor concentration, okay? And that's then is the third bar. What you can see that the standard, the EN standard, which is based on the perceived air quality, it's good enough for the CO2 concentration because the flow rate is double that, looking at the bar, at the column, sorry. Then we have the ASHRAE 62.1, you see there, the lowest flow rate. And then you have the green one, which is instead the proposal for the health-based ventilation in the EN, which is the gray one. Then you have the ASHRAE 241. You see the yellow, which is higher. That means the required clean airflow rate is good enough compared to the green bar, the calculation. And then the latest one, forget it's the Italian one. But what I'd like to show now, that if I'm going to change the virus, or if I'm going to change some of the other parameters, all the other column will stay exactly the same, while the green column will change. You see now? This delta variant, the other disappeared. That's the problem, that when you have a table without specifying what kind of virus, it was tuned on the ASHRAE was tuned on the original one virus, but the Delta variant is, or the actual variants which are similar to Delta variant, is much more effective. And then you see, fortunately, the effect is much less important on humans, but the infectivity is much higher. But then you can see there what I mean, that if you have a standard which is based on table which is prescriptive, cannot be good for any situation. If you have a performance standard, then instead you can do what you need, and you can compare, and you can see what's happened there. Then you can see there are some other examples. This is the worst, meshless. No, you can see there. The bar is still higher, and the other disappear. It's just to give an overview again, and then you can see sorry, the different situation here, no? Different virus, SARS-CoV-2, 1, SARS-CoV-2 Delta variant, and meshless, no? The different columns. And you see, of course, there is no difference with any of the usual method we can use for designing the ventilation system, while you see the difference according to the virus. But it's not only a matter only of the virus, because you see, if I'm going to change now the probability, the risk probability, then I get different result. Now the difference is lower because I'm accepting different risk probability, and so on. This, I'm changing the exposition time to 1 hour. This is the same, 1 hour, but RE is 0.5, and the risk probability is 2.6, etc. This is just a very important slide, the last one, because I was just looking at the idea at the beginning was, why not to show that if we have a good ventilation system, clean air ventilation system, we can just reduce, let's say, sick leave, or we can reduce, can increase productivity, because, for instance, we just take care of the most common virus, the influenza. The result was very interesting. You see there that the health base is just saying that if we are in normal situation, I mean, I'm not really loudly speaking or not making some chimney or whatever, the needed flow rate to have a very low risk for influenza is completely covered by any standard. This very interesting result is a key to say, go to ventilation, because you will be repaid back but the fact that you can increase the productivity, no? You can reduce the sick leave period, and so on. Then, and the other lesson learned, as I said, that we have to move, as we discussed before, to performance-based design and to leave out the prescriptive-based design, because we are coming to close to, we are improving so much everything that we cannot rely on a table today. But we have to take into consideration all the degree of freedom we have and all the potential we can use, not to have a better environment. Thank you for your attention. Just to say thanks to the people working on the main engine. There was the group of Misleschi, Bonanno, Stabile, Pacito, and Lidia Morasca. Thanks a lot.
We can take one quick question from the audience. Yes, sir.
A lot of detail in the presentation. I was particularly interested in the use of air cleaners, which is a big subject within ASHRAE and the Environmental Health Committee, which I'm involved in, because you were talking about from 241 putting outside air coming in and the cost of that. Air cleaner seems to be one very significant part of the solution as an additive mechanism to provide an additional engineering control that then allows you to see how the data pans out in reality based on actual measurements from formulas.
Just to be clear, what I've been showing here is the target value. Then you can reach this target value with any system, with outdoor air if it's clean, or using cleaner system. That means it can be also box in the room. Eventually, depends on the situation. This was just to provide the design airflow, okay? And then the engineer can choose according to the specific situation. I would say that if you are in a school, you cannot design for the maximum flow rate. You see, it's a very, very, very large. No, then what you can do, you say, okay, maybe I will have 1.2 or 1.5 more than what I'm going to design with the ASHRAE 62.1, and then I will have a standby system with an air cleaner, 2 air cleaner, 4 air cleaner according to the situation. If I have a pandemic or an epidemic, then I can bring in and can run it. I mean, this is just to change the way to think about the design, because you are able to design a system with a burst, maybe double fan, and then you can double, but also a problem with the channel, you cannot size too much. No, it's a cost. Then you see it's coming in the business. As a kind of backup system, you can take in the play when you need it, not when you don't need it.
Great. Thank you.
Thank you.
Thank you. Thank you, Professor Massarella. We have the certificate of participation for all participants, and I would like to ask you, please, to keep your presentation up to 15 minutes, so we will have also the chance to have at least one question for every presentation. Our next presentation is IQ, Comfort, Health and Energy. Can we have it all? By Igor Mujan, professor from University of Novi Sad. Igor, please.
Good afternoon, everybody. I have a broader perspective on the indoor air quality. This should be a breakdown where we're at with indoor air quality and the changes in the past few years that have made indoor air quality a requirement, not a comfort or consideration when designing high quality buildings. So, as we all know, we spend majority of the nowadays indoors, about 90%, so even some groups have 100% indoor exposure, and we have to think about consideration of the indoor environment quality. Also, we have some, let's say, clear evidence that indoor air quality, thermal comfort, acoustics, and lighting have measurable and cognitive impacts on human well-being. However, we cannot just say that those are the only impacts of the indoor air quality. Often the stress related to the work environment or other aspects have the same impacts as the indoor environment quality, and also we have a problem where majority of the time we talk only about the effects of the environment that we can control in some way and are measurable. However, other aspects should be also considered. In that sense, we have multiple, let's say, checklists to determine whether the indoor environment quality is acceptable or not. However, we do not have a clear goal what and how it should be measured, whether it would be one index or we should have multiple checklists that all need to be crossed off in order to have the acceptable environment. Also, the expectations of the occupants in the buildings has increased dramatically after the COVID. Prior to COVID, majority of the occupants in the working environment didn't know what was their environment like, what were the conditions needed to have a healthy building and to prosper and have well-being in the building itself. Also, we have the recast of the Energy Performance Building Directive from 2024 that now includes the indoor air quality as core energy performance. So we cannot talk about independently about energy efficiency and indoor environment quality. We have to make a connection between them and find the optimum solution, because in the past we have seen them as competitors in the building environment. So we also have problems. How do we define indoor environment quality? So if we look at some of the let's say high-performing building standards or schemes, we see that more of the indoor environment aspects are needed to be met in order to have a proper indoor environment quality, but the directive only sees the four aforementioned key aspects. So we also have to find the formal definition of indoor air quality and also how to integrate it across design, renovation, inspections, and energy ratings, and also monitoring after the commissioning. So we have multitude of problems. However, we are now in the era where we need to connect the design with the monitoring and the real-time performance of the building in the later years. So this is also problematic. How do we make EAQ indexes for the multiple different building types? For offices and buildings, let's say in the commercial space, we can do that as we can standardize them. However, for the building stock, it's problematic, and we do not have answers for that yet. So now we have to have them coupled, for instance, energy and indoor air quality. Also, in the past couple of years, the majority of research has been done on the indoor air quality. In some sense, thermal comfort is something that we seem to understand, even though the research has picked up in past couple of years. So we need to control now CO2, PM2, or particles below PM2, and VOC coupled with thermal conditions. And also we need to have the lighting conditions under control, and also glare is very, very important. Also noise is very underrepresented currently in the standards, as it's often mixed with, as I said, psychological conditions and stress related to the work, and we have problems, and we have very little understanding at what noise levels are acceptable at different circumstances. So we have to look indoor air quality as multiple domain exposure. We cannot look at it as a checklist that we can solve separately. We need to find a solution to holistically look at indoor environment quality. So also, for instance, we have seen some confusing data in the past couple of years. So we have seen that lowering CO2 below the acceptable, in the past years, acceptable levels below, for instance, 1,500 ppm. We have seen higher cognitive performances in buildings. However, the studies show that during the COVID, we had masks with 20,000 ppms, which didn't lower cognitive or performance of people wearing the mask. So we have also confusion, and what a CO2 means. Is it really a performance index, or should it be just an index that indicates that the quality of indoor air is getting lower? Also, we are diving very deep into indoor air chemistry. As sensors get cheaper, we can go really deep, and we can understand the environments much better, and the scientific community has the tools to do it. So also infiltration domains are very different across the standards. As Professor said, we have very different values when calculating necessary indoor air infiltration or ventilation rates. So we also can evidently categorize indoor air quality based on the health risks and the cognitive performances of occupants. Also, in the past couple of years, we have seen, or 10 years, we have seen the multitude of new thermal comfort models, because we have seen that the old kongres model doesn't really apply to the scenarios in which we don't have controlled systems, but also we have to find the solutions for building stock that is not subject to that model. So, for instance, different climates and occupancy rates created a whole separate branch of thermal comfort, and we have, for instance, 7 models that are applicative. Some of them are even in the standards. For instance, Chinese use their adapted thermal comfort for calculations. Also, there is a problem that for instance, thermal comfort and indoor air quality are interconnected, and also, for instance, increase of temperature changes how the particulate matter, odors, and other chemicals in the environment work. For instance, majority of the time in the laboratory, we use constant conditions and cannot replicate every component that is dynamically changing. Also, so as I mentioned, visual and acoustic comfort are often underrepresented. Glare is certainly a very problematic topic currently, as the influence of direct sunlight can have similar effects as decrease in thermal comfort. And also, we have seen that some studies connect even noise in the buildings. They connect noise with thermal comfort, so occupants show similar sensation to the increase in the noise as they show the discomfort in the increase of temperature. We need to understand now the interdependence of energy efficiency in indoor environment quality. They competed certainly in the past couple of decades, but now we need to find the optimal solution. So we need to find the optimum between air tightness, mechanical ventilation, and so on. So over ventilation, we have seen multiple studies that show that over ventilation can be reduced if we concentrate on the pollutants in the environment, and we can then increase the energy efficiency. Okay, and the energy performance building directive now tries to make us find this optimum, and this is the roadmap that should be followed. Also, we have the problem that we design buildings that often, as also Professor said, change the scheduling of the occupancy or the number of occupants and so on, and we have to then continuously monitor the buildings to see whether the design has met the goals, or we need to change the ventilation rates or the system itself to meet the new needs. Also, the decrease in price of the sensors that now is, for instance, sensing the temperature, CO2, and the relative humidity is around 10 to 15 euros per sensor. It's really cheap, and we get high resolution results. We can do continuous commissioning, which we couldn't do now. It was done periodically once a year, and it will really increase what we understand about the indoor environment quality in the buildings moving on. So we need to see what's the operational reality, and also we need to see how the indoor environment quality changes during the commissioning of the building. Also, we can use the knowledge about the indoor environment quality to detect anomalies. Multiple studies have shown that that anomalies in the reading of the, for instance, CO2 can show that we have the anomalies, for instance, dampers not working in the system and so on, even though all the parameter systems really work. Also, what will be our new, let's say, companions in the upcoming future will be end users, because of the low cost of the sensing and the free applications that integrate those sensors in, for instance, home assistance, for instance, ESP Home. Users are empowered to create their own smart homes, and you can see, for instance, with the sensors that cost 10 to 12 euros, end users put them in every room and collect a lot of data, which can then be used again by us to determine the values that are achieved, for instance, in different types of homes. Also, that comes with a risk. The end users are not knowledgeable about the use of the sensors, and often there is misinterpretation of the readings. For instance, a lot of the sensors that are cheap, really have high resolutions, they are not out of the box, they're not calibrated. So we need to do the calibration. After the calibration, the sensors work well, but they alarm the end users that something's wrong. Okay. Yeah. Also, so those are the risks, and we cannot be ignorant. But there are, for instance, opportunities. So designers, we have to have the early integration of the comfort and energy, and also monitoring objectives, and also operators need to do the continuous commissioning using the systems, and also users are now empowered to participate in maintaining healthy indoor environment quality, but also we need to teach them how to work in this environment. So we have to create a whole new ecosystem. So this, we need to align as the domains stage, and in conclusions, we need to, in the next decade, have the co-produced EAQ, so regulation, engineering, and users with their tools. Thank you very much.
Thank you, Igor. We have time for one short question, please. Two, but very short questions, please.
It's very, very short. Realistically, monetary realistically, separating commercial from non-commercial, is there a difference? I think it's a lot easier to monitor indoor air quality in non-commercial. In commercial, I mean.
Yeah.
How do we handle the multitude of residential buildings?
Well, thank you for the question. That is the main problem. If you have one owner of the building, you can integrate monitoring across the whole building. That's easy. But if you have multiple owners in the same building, it's problematic. Given the fact that they all have different understandings of the indoor environment quality. So the objective, maybe the sensors are so cheap now that through municipalities, maybe we can integrate them in the end users' homes. And also, for instance, I did a lot of the field studies. When you speak to the end user, they change their own mindset about the indoor. They want to become a lot more knowledgeable about the environment. So it would benefit them to know what their environment is. Also, everything that I've talked about has the security risks. We know that we are in the cyberspace now, so all those systems can be now hacked, controlled, and so on. So that's another layer that needs to be also considered.
Thank you.
Do we have another question?
Yeah, I was very simple. In the beginning, you just said that you don't have to consider separately the four pillars of the environmental quality, but in a holistic or integrated way. What do you mean with this? Sorry, I will be clear. Just one unique indicator?
So we have to, let's say, decide what we need to make that indicator, because in the academia world there's two parallel lanes. One is telling us do the checklist of separate indicators for each category, because we say all of these indicators are from the responses of the occupants of the building, and they were done. But also the other tries to make a polynomial that integrates every, but then you have the second, let's say, double occupant answers for the same question.
The second doesn't work.
Yes.
There was a project in Europe funded by the Commission, ALDERA, and it's very clear the result, and then you have to consider the four indicators separately, and the quality of the environment is related to the worst.
Yes.
Because what
Yes.
you feel, if you have here, for instance, a lot of noise, you don't feel the air, you feel just what is worse.
Yeah. Yes,
What is the result? A box with
Yes.
different colors, different quality, and the worst is the dominant.
Exactly. I wanted to. That's the tail index. Tail index, yes, and they're the most rigorous. The worst one is what you see. Yes. I agree with that.
Thank you.
Thank you.
Okay. Thank you very much, Igor. We are following our program. The next presentation is coming from the group of authors from Banja Luka, and the author and the presenter is my dear colleague Milovan Kotor. So please, the floor is yours.
Thank you. Hello to everybody. I will give you presentations, comparative analysis of CO2 concentration by natural mechanical installation in education buildings of the University of Banja Luka. This paper was prepared by a team of 9 senior and young researchers from the University of Banja Luka. And the presentation is written in English, but for me it's easier to express on local language. If it's not a problem, if it is a problem, I will continue in English. So, my choice. Okay. So let's continue on local language. So,
Is
Can I
there
say
a
go?
translation? Do you have translation or not?
Do you have translation? Ah, yes, I didn't start. Okay. Channel 4. Igore, sljedeći, treći. So, could I start? Let's go. Rad prikazuje je dio istraživanja jedne studije slučaja koja se bavi kvalitetom vazduha u učionicama Univerziteta u Banja Luci. Znači, generalno on se oslanja na ove prethodne dvije prezentacije koje smo slušali, a cilj ove studije jeste da se u principu utvrdi kakav je trenutni kvalitet vazduha u učionicama i kako da ga unaprijedimo u budućem periodu. Kao opitni uzorci, tako da kažem, izabrane su dva objekta. Jedna učionica u jednoj starijoj zgradi u kojoj nije izvršena energetska sanacija i u kojoj imamo prirodnu ventilaciju. To je ova zgrada, sad ne radi ovdje laser, znači to je ova donja zgrada. To je zgrada fizičkog vaspitanja i sporta koja je konstruisana 60. godina prošloga vijeka. I druga učionica je amfiteatar Arhitektonsko-građevinskog fakulteta. It is not possible. Okay. Okay. Let's start. Yes. Generally, this paper presents a part of one research case study at the University of Banja Luka that based on indoor air quality, indoor comfort in the main amphitheater of the Faculty of Architecture, Civil Engineering and Geodesy and Faculty of the Forestry. This building is located in the Faculty of Physical Education and Sports in Banja Luka. So generally, this study are conducted under Horizon Tvidera project, enhancing scientific capacity for energy poverty, coordinated by the University of Banja Luka. Generally, this paper runs on two sources. One is the questionnaire distributed among the students about subjective feeling of indoor air comfort, indoor air quality. A second, measurement of CO2 concentrations in the classroom of the Faculty of Physical Education and Sport and in the amphitheater of the Faculty of Architecture, Civil Engineering, Geodesy, and Faculty of Forestry. So, to say something about this building, the Faculty of Physical Education and Sport was from 1916s, and generally, according to current rule book of energy audits and certifications of buildings in the Republic of Srpska and in Bosnia and Herzegovina, belongs to energy class G. Second building is the building of the Faculty of Architecture, Civil Engineering, and Geodesy, and Faculty of the Forestry, and according to the same rule book, these buildings belongs to energy class B, which corresponds to category of low energy consumption buildings. This is lower building, you can see down. So why is indoor air quality and CO2 concentrations in the education building important topics? We know that indoor air pollution has huge impact on human health and well-being, and also on students' concentration and ability. In education building, this topic is particularly important because students are more vulnerable to poor air quality. We know that carbon dioxide is naturally present in Earth's atmospheres, and usually concentrations of CO2 and odor depends of industry activities, traffics, and usually are between 300 to 500 ppm. In indoor environment, concentrations of CO2 rapidly increase due to human activity and have impact on indoor air quality. The increase of CO2 concentration depends from many factors, from the size of classroom, number of students, its activities, ventilation rate, and etc. Generally, CO2 concentration standards and guidelines are different for various countries, but limit prescribed values generally set between 1,000 and 1,500 ppm. We use two approaches to assessing air comfort. One is subjective perception by the questionnaire, obtained by the questionnaire. Second, this is a measurement of CO2 concentrations. This was carried out in two characteristic buildings. One old building with natural ventilation. This is building of the Faculty of Physical Education and Sport, and the second building is the building of the Faculty of Architecture, Civil Engineering, and Geodesy, and the Faculty of Forestry. So during the measurement, you use appropriate standards, and the measurement locations for indoor concentration of CO2 was chosen to ensure that results present a representative value, unaffected by source like students or room ventilations. The position of measuring device you can see on the left figure for the Faculty of Physical Education and Sports. On the right figure, you can see position of measuring device in the main amphitheater, the Faculty of Architecture, Civil Engineering, Geodesy, and the Faculty of the Forestry. This is the blue punct, which red are marked the seats students when we distribute them the questionnaire, so say. So for the first building, all building with natural ventilation, measurements were taken from November 1st to 8th, 2024, and we have more than 3,000 measurements. For the second building, new building with mechanical ventilations, measurements were taken from November 25 to December 5th, with total more than 4,500 measurements. So which are results? To say something about results, generally, if we discuss about Faculty of Physical Education and Sports, according to measured concentrations CO2, the quality of indoor air was in the category 3 mostly, and in the category 4. And in the case of the Faculty of Architecture, Civil Engineering, and the Faculty of the Forestry, the concentration, the quality of indoor air was mostly in the category 2 and the category 3. How about survey or questionnaire obtained by students? The survey was conducted in the first building on the November 7th, and we have 16 students very surveyed. For the second building, the building with mechanical ventilation, the amphitheater of the Faculty of Architecture, Civil Engineering, and Geodesy, the survey was conducted during the 2nd December. In the first building, we have 16 students. In the second, 62 students. As you can see from the table 2, most students are females, and average age was about 21. What about air quality? Most students from the Faculty of Physical Education and Sports thought that indoor air are polluted. Different from other hand, most students from the Faculty of Architecture, Civil Engineering, and Geodesy, and Faculty of the Forests thought that the air quality is good. On the next figure, you can see results of measurement CO2 concentrations. And as you can see, the highest value of CO2 concentrations in the Faculty of Physical Education and Sport was more than 2,000 ppm. And in the Faculty of Civil Engineering, Architecture, Civil Engineering, and Geodesy, in the Faculty of Forestry, was about 1,400 ppm. So with S is marked the day when we have a questionnaire, we distribute questionnaire between students. As you can see, for the first building, the building of the Faculty of Physical Education and Sports, during the time when the students answer on the questionnaire, the concentrations of CO2 was almost 2,000 ppm. And in the case of the Faculty of Architectural, Civil Engineering and Geodesy and the Faculty of the Forestry, the concentration was below 1,500 ppms. This is approximately the category 3 or 4 for the Faculty of Physical Education and Sports, and the category 1 and 2 for the Faculty of Architecture or Civil Engineering and Geodesy and Faculty of the Forestry. So this table shows us the maximum and minimum concentrations in the Faculty of Physical Education and Sports and the Faculty of the Forestry. Generally, how we can explain this result: volume of the amphitheater in the Faculty of in the Faculty of Architectural, Civil Engineering and Geodesy is 3.22 times larger than the volume of the classical lecture room in the Faculty of Physical Education and Sports. So that explains why for almost the same number of students, we have lower concentration CO2 in amphitheater compared to concentrations in the classroom in the Faculty of Physical Education and Sports, except that in the Faculty of Architecture, Civil Engineering and Geodesy, we have mechanical ventilation system, which was turned on. So he helped provide fresh air for the students in that time. So generally, conclusion is in line with measurements which confirm that generally when the concentration CO2 due to high concentration CO2 in the classroom of the Faculty of Physical Education and Sports, we have worst quality of indoor air, and that means that students are not satisfied with air quality. And opposite of that, we have less concentration CO2 in the main amphitheater of the Faculty Architecture, Civil Engineering and Geodesy, and we have better answer of students. They think that are in this amphitheater is good. So
thank you.
Only one thing. I thought that this project, this case study, is a part of one Horizon project. Please follow us on the web, Facebook, Instagram, LinkedIn, and YouTube. Thank you for your attention. Maybe I didn't explain something important, why we conducted this study. We have question why. The goal is to see what is present condition, what is the quality of indoor air in classrooms and in the amphitheater. Why? Because the Faculty of Physical Education and Sports past process of renovation. And we want to see how change the quality of indoor air before renovation and after restoration. So this research is the first step of this comparison. For the Faculty of Architecture, Civil Engineering and Sport, we have another problems. The problems was that mechanical ventilation units spend too much energy, and the most time the ventilation unit doesn't work. So when students have a feeling that the quality of indoor air is not good, then turn this unit on. So we want to help the faculty to save energy, and from the other side to improve indoor air quality. For the Faculty of Physical Education and Sport, I think that will be more problems than now, because they, with all the windows, have problems with CO2 concentrations. After renovation, I expect more problems. That means that concentrations of CO2 be higher than when we measured in our research during 2024. Thank you.
Thank you very much. Do we have a short question, please?
More than a short question, a simple suggestion. First of all, forget about natural ventilation.
Yes.
Because you cannot control everything. Second, it seems that the ventilation, mechanical ventilation, was not well designed.
Yes.
Then the first things you have to do, just take one of the standard we discussed before and check what ventilation rate you should have. And then you can compare with your data to understand if the correct design according standard A or standard B is good enough or not. This will drive you to the correct design for the retrofit.
Thank you.
You're welcome.
So, as I know now, mechanical ventilation unit is designed for 21 or 22 cubic meters per person now. But obviously that is not enough if the amphitheater is full occupied with students. We have about 118 students. It is too small amount of fresh air. Thank you for your
Thank you. Thank you again. We'll move now to our next presentation. I'm going to invite Dimitri Haralambopoulos. You see how good I am with Greek names? Who else could have pronounced this name? So Dimitri is a mechanical engineer and an active ASRE member and actually member of ASRE Environmental Health Committee. And he's going to be presenting improving the environment and health in buildings.
I think I'll have to change my presentation on the fly with all these things that everybody has talked so far. And it's nice that we hear about ASRE. ASRE is an organization. I feel it's a tool at the disposal of every engineer. And on the left, you see the outline of a bust of goddess Iyea, a Greek goddess. That means goddess of health. And hygienic comes from her health, and you'll see it many times. The abstract, I'm not going to read it. It's general for you, up to your level. I'll try and start from the basics and try and build up. We need to take out all the work that's been done in academic level and in ASRE to everyday use. So what's the purpose, really? We need to improve the indoor environment quality. That's the first step. The second step is to improve the IAQ, air quality, and then the indoor environment quality, and then the health that covers everything else. In the IAQ, I have included some more factors that might be applicable in several areas, like ergonomics, aesthetics, water quality, EMF levels, and occupant control. So it's a long discussion, and we have to do it on a more organized way. Now, in the field of health that in my mind covers the previous two sectors, the IAQ and the IQ, because you have to have them in order to speak for health. We can distinguish them into two main categories, external hazards and the internal hazards. Now, the external hazards can be subdivided into ordinary hazards, like low outdoor air quality and pollution, and extraordinary hazards like wildlife and pandemics. It depends on how we tackle each one of them and the result that we are going to have indoors as a health. The internal hazards can be classified into chemical, biological, physical, and ergonomics. Most of these that you'll find in ASRE publications, and I will be referencing them later on. Now, external hazards. We need, first of all, infection risk management mode that the systems of HVAC will be ready to be activated and be prepared to act upon the level of the threat. And we're going to talk about a little bit of the equivalent outdoor air for infection risk mitigation when there's a pandemic or whether there's a wildfire. It started becoming a bit more common. Wildfires, you know, we had them in the States, a lot of that. We had them in Canada. It affected our health, not our in this room, but the health of our colleagues. And then we need to have a mitigation business readiness plan. Sometimes they put a lot of sensors, and sensors, if there's a critical condition, they light up. You know what's the first thing that they do, engineers or the people responsible, administrators? They turn them off because they don't like to see all these bulbs lighting up, you know. Perhaps the solution would be if we try and build an AI system that we prioritize the level of importance from a sensor and which we should look after first. Some of these thoughts come from the admiral that in a Navy ship, they have lots of threats, and the system has to decide which is the most obvious one, the one that you have to respond to first. Equivalent outdoor air, I've just given you, it comes obviously from ASHRAE Standard 241 that we've discussed before, and you can have an indication of the air that's needed per activity per room. I have to say that during the pandemic, it's important to see how fast a system can respond into this condition, into an emergency. ASHRAE reacted with an epidemic task force during COVID, and just out of fun, the site that they had put up on the measures that they could take had billion visits, billion, not million, billion visits during its lifetime, during and after the pandemic. And another fun fact about Standard 241, it was prepared in 6 months, which is a record time for a standard. That means that society needs to act fast into emerging threats. Now, internal hazards. We have chemical hazards, which is the nature of potency. We have biological, we have physical, and we have the ergonomics. Internal hazards have a lot of causes that they appear. It's the lack of quality control, the moisture, poor outdoor air quality, moisture and dirt in ventilation systems, indoor contaminant sources, inadequate ventilation rates, and ineffective filtration and air cleaning. We say them, but do we apply them? Do we maintain them, or we forget about them? There are many cases that we might prescribe filters or HEPA filters, and then they forget to clean them, or the maintenance guide just bypasses them. There are cases that have happened not only in Greece or perhaps here, but in the UK, the US. A Canadian colleague said that he had installed HEPA filters in a hospital in almost all of the patient rooms, the ICUs, and the operating theaters. But he forgot to put them, or he didn't think he should put them in corridors. And later on, corridors were full of patients in beds because they didn't have any other space. So we need to think holistically about health. And probably in a hospital, it needs to be seen as one unit. No spaces left outside, not discriminate that. Having said that, health, the best line I've heard from a doctor was, health starts at home and ends at the hospital. So there are a lot of steps that we can improve human health. And this health initiative is driven basically by insurance companies that in other countries are paying premiums, and by the absent days from work due to health, that they monetize these effects on poor health, and then they started demanding better health on the buildings. Internal health, we did say, and discussing how we can improve health, we found out that we need to talk with other professions. We as engineers have a limited, in my mind, view. In my youth, I was a design engineer for public works, and I've done quite a few hospital designs. I never was in contact with any doctor. Then I had another colleague that he was responsible at the hospital. He would give me the parameters and I would design it, and that would be it. Now that we've started, last year we had a session on health and safety in one of our conferences, the energy in buildings, and we had doctors that changed my perception of what we should do and what we have to look into. So we need to bring into the room other professions as well. Internal health, chemical hazards, VOCs, volatiles and semi-volatile organic compounds. Connor is with me at the Environmental Health Committee of ASRA. We've discussed that. We did last year's handbook has on chapter 10, it's been rewritten and updated. We have biological hazards, and then we have physical hazards. Let's not talk about the physical hazards, but we have to have them in our mind. Internal hazards, chemical, risk depends on nature, biological, I think it's the same one. No. How do we confront the internal hazards? Regular cleaning, disinfection, hand hygiene, use of barriers, environmental controls, proper waste management, and avoid cross-contamination. Simple, isn't it? Life is simple, I think. And then the best part is education and protocols. We need to educate everybody, from the doctor to the patient to the common person, what they should be. We don't do that, not in my mind. Thank you. Peace to you, brother.
Peace to you too.
Again, the internal hazards, I've written on the left the method how we treat them, a description and the action that we need to take. I'm not going to read through that because he showed me the victory sign. Just for the fun of it, we have carbon monoxide. We know everybody, we know about that, we know what we should do. Do we have deaths from carbon monoxide? You bet so. So we don't follow that, right? Internal hazard infections. Contact transmission, we said that before. We said how to control it. And again, we have the control of infections, aerosols, the standard from ASRA, that it's been talked before, so I'm not going to go again onto this one. And again, these are the ways that we have to tackle them. For your use, you can have this, for the people that are not very familiar with all the ASRA work that's been done. From 2025 ASRA Handbook of Fundamentals, you'll find chapter 10 quite interesting. There's 241 and method of commercial and in room air cleaning device and systems. And I would like to touch a little bit on Legionella. A couple of years ago, there was an outbreak in New York, and I think they had 7 deaths. Now, would you say that you have deaths from Legionella in Serbia? There are in other countries, maybe in Greece. I'm just saying maybe to cover my... And how do we explain it? Or do we declare it? No, we categorize it as death by pneumonia, which has similar symptoms. We need to look after that, and especially with the data centers that they were talking, they had lots of water and big sources from Legionella if they are not treated properly. So another set of ASHA standards that you might useful for your job if you are improving the health side of your design and profession. And some of the topics that they are on chapter 10 of the handbook that you might have a look. I think in our world, we have the 4 Bibles, the handbooks of ASHRAE. And then what's the next step? Are we finished? Is this enough what we are talking about? Of course not. So what's the next step of this long journey? I'm proud to announce I'm advertising now this conference that will be in Greece. It's the first of its kind, as far as I know, that will bring the medical and the engineering world together, and hopefully will start a continuous discussion that could move to other countries and other places of the world, that we take a holistic point of view of health. We need to have open discussions on many subjects, not only one. It's very limiting to have it just in one session about health. And that's what I would really like to say for today. There's this also, if you want to learn some more and if you want to join, you're more than welcome. And if you want to join, and if you have something to say for joining us, please do. Thank you very much.
Thank you. We can take one quick call question from the audience. No, everything
Perfect.
was
Thank
crystal
you.
clear. You're good to go. Thank you.
Thank you. Our next speaker is Georgios Bamplenis with presentation bringing civil or military preparedness, strategic prearrangements for WMD events, targeting public health infrastructure.
So, good evening, everybody. I know that it's already late and tired, everybody, so I'll try to shorten the presentation as I could. I will start from what Dimitris mentioned previously. What is the next step? The next step, as defined by the Secretary General of the United Nations General Assembly, is that we now face a world where threats are increasingly asymmetric, terrorist groups, hybrid actors, and technologically empowered non-state entities are more capable than ever to targeting our infrastructure. So we build our infrastructure in such a manner that is efficient, with very low energy consumption, increasing the well-being and everything. But what about security? Only two people in this room today mention security. Dimitris, by discussing about hazards, and the gentleman from Israel, Avi, if I remember well his name, he said that we build our data center with 3 meters of concrete because the enemy is outside our door. And how far from our door is the enemy? Look at the map. This is the global risk and security assessment, areas with high risk. All those can affect our lives. And how? In a manner that we can predict, we can control, and we can avoid. So the growing instability of WMDs means weapons of mass destruction are things with low cost, uncontrollable, and with no restriction in catastrophe. Asymmetric actors are between of us, and all the big organizations had issued doctrines how to defend in such a case. So it is obvious that not a single actor can undergo such an event. The NATO is talking about interoperability and common terminology between the civilian and the military sector. The military sector actually is the only one that has the knowledge and the machinery to react in such a case. The World Health Organization says that health needs security and logistic support, and the EU action plan is that a pre-arranged coordination is needed. Down below you can see the NATO doctrine as exists today, and it is on the internet, free for everyone, and in the other side, the Health Organization doctrine, the World Health Organization doctrine. What do we have to do? We understood from the distance between military and civil sector that we have to improve our cooperation in such a manner that we have to be integrate our command systems without affecting the security of the systems, of course. We have to share our awareness about the situation, how possible is the risk, who has the information, more than the military and the information facilities. To combine our capabilities with the existing systems in the military sector that can define and detect the threat early enough to give us the time to get prepared, and of course to resolve the legal issues. There are major legal issues in such an event, in such a situation. And finally, to unify our risk communication system. We have to pass the information to the civil sector that they have to be ready to defend in a threat such as whatever it is. Those are critical infrastructure in the far end of the slide. And the critical sites that affect our lives are, of course, the hospitals, the labs, the emergency operations center, and the government and ICT hubs. If we don't protect enough them, and we don't have a capability to address people that know what to do to get connected in our facility, I'm afraid that we shall lose the game. And we've seen that. In the COVID era, we are not capable to undergo the situation because we didn't have the capability. Those are some let's say, bullets coming from the studies of the military sector that needed to adopt the civilian in order to improve the security of our system. So high integrity filtration, overpressure zones, very, very essential in the COVID era, radiological sealing and protecting our intakes. Imagine if someone steal the mask from a radiological consultant and put it in the air inlet of a big hotel, nobody will understand that because nobody ever thinks to install a $200 detector that will give a very good prediction and information. Mention the sectors, the power redundancy, water needed always, and of course, control access and decontamination, whom on the civil sector before COVID has an idea on how we manage the entrance or the exit from a control area? None. Exercises. The only way to get familiarity with such a situation is to do common exercises. In the beginning, when I was participated in an exercise in London just before Olympics Games for managing such a situation, it was a disaster. It was proven that we didn't have any capability and any possibility to cooperate together. With a lot of pressure and with a lot of training, we are now in a position that we say that we have the basics. But what needed is for us, the designers, the supporters, to adopt that with an enemy undefined, anteportas, we have to get prepared for cooperation with the persons that they know how to do it. If you can see, the NATO doctrine is translated in Cyrillic language. Above is the English version, below the Cyrillic language. Conclusion, we have to get prepared from before. Predict is better than cure, was the saying of Hippocrates 2,000 years ago. Protect our health and other important infrastructure. Prearrange the framework from resilience and survivability. And preparedness start before the crisis. Thank you very much.
Thank you very much. We have time for one short question, please.
Okay, thank you once again. And we will proceed with the last presentations for today. We will have presentations for our dear colleagues from Romania. So I invite our colleague Paul Danca to present the paper.
Okay. Good afternoon, everyone. Thank you for resisting until this moment. I'll make a presentation about some studies made with my colleagues and with the financial support of Renault that was interested in this, on the results from this study. And through this study, I want to highlight on a side that the environment for the vehicles is a particular, and that the methods to evaluate this environment are not so adapted to this environment. Why? Why is this so particular? A few moments ago, here inside, I feel that was very hot. It was. Somebody, another opinion. Let's say, everyone agree? No. Yes, not. So we can say that thermal comfort is a state of the mind, right? Even if we have neutral condition, not all the people will feel the same. And we are in the protected environment. We don't have solar radiation. We don't have fans or blowers or air passing near to us. So this environment is in the I don't remember the word, but it's a steady state condition, right? On the other side, the environment from the vehicle is very transient, non-uniform. Maybe the passengers from the front can feel better, the passenger from the rear part of the car, so on. More than this, we now see that mobility is part of our life. We have to use a car or a bus or something to go from a part to another. This is the reason of my study. And what was our proposal? we introduced it as the diffusers. We changed the geometry of the aileron of the diffusers, but it's not working. With ailerons. Why? Because some studies made some years ago, some colleagues showed that these ailerons introduces transverse shears that are improving the mixing between the air from an environment introduced by the ventilation system and with the air from the environment. So I was thinking was that if we will implement this solution, we'll have a better, more uniform environment, and we will reduce the draft, let's say draft sensation, but this sensation given by the air blown by the ventilation system, who is passing across near to the hands of the people in the front seat. And this study was performed, the evaluation of the environment, from the thermal environment from the car was evaluated with in three ways, with the passengers who filled questionnaires with questions regarding thermal comfort at the local level, at the whole body level, with a thermal mannequin was manufactured in-house, and with some standardized tool is a comfort sense, which give us the PMV index, predicted mean vote index. And we wanted also to understand more and better the phenomena from this environment, and a numerical model was performed with the mannequin placed on the driver's seat. On the other hand, as we know, this measurement tool, which gives us the PMV, it considers that the PMV achieved in a single place in the room or environment will be considered to be in all the corners of that environment. That way, we place it in the driver place and on the center of the car, in the center of the car. Good. Our car, our test was for 50 minutes. Was a car without automatical temperature control inside. I mean, we could change only the ventilation, the flow of the ventilation temperature. And we made for the 3 steps of the ventilation systems. And we can see here also the values, the mean values of the flow introduced by this ventilation system used. Then we used only the blowers from the panel. As you know, at the car we have for the frost, for the foot, and we have the central. We use only that because we was in the summer period. And a series of sensors was installed inside the car to measure the temperature. Some of them was wireless, some of them was thermocouples. The thermal mannequin designed in-house had 79 zones. With this, we can determine the equivalent temperature index because he can determine it by knowing the heat released by different parts of the body. He is split it in 7 parts. 7 was? I think 7, yes. Hands, foot, and so on. No, it was 60. 60 parts of the body. Good. After that, the numerical model was performed a mesh test to see which one of the mesh are showing us the real results, and are the results achieved, not real, are more closer to the real results measured. And we was using first a preliminary measurement session to validate this model, and there is a paper already published regarding this. For the study, for our study, this was the inputs for the numerical model, and here we have some results regarding the temperature achieved in different parts of the car, on the surfaces, and we can see V1 CD means from the bottom. V1 CD means velocity 1 classical diffuser, and that aileron rob diffuser with red in that case. And we can look here on this graph that the lower temperature were achieved not everywhere, but was achieved, for example, in the first case. And after that, we can see for V1. And for the dashboard, for example, we can see that is lower in the case of aileron diffusers. We may put this on the hand that the mixing provided by these diffusers is better, and the temperature of the dashboard and of the other parts of the car is decreasing. Let's think that the session was only 15 minutes. After that, the temperature at different parts in the car, at the head, knee, and chest and foot level, shows the same. The mean temperature for the innovative diffusers is less than the other one. And the results from, and here we have some results of air pad velocities. And we can see that in the case of the diffusers, the classical diffusers, right? We have a lot of the velocity of very concentrated, I have high velocities near to the dashboard. Meanwhile, comparing to the other case, the velocity are less, and the flow, the velocity, the mean velocity is kind of, is more well distributed inside the vehicle. We can have also, you can see also the draft index distribution on the right, and we can see that the areas with the draft rate value negative, who provoke a negative state, are higher in the case of classical diffuser. Here we have the results regarding the PMV vote. And again, in the front part of the car, for the lobe diffuser, we can see that the green means good state, it's around 0. Meanwhile, we can see here at the chest level and at the head level that the values are showing a kind of negative, a kind of cold state. And here in the above, we have the values achieved with the thermal mannequin, are the values of the draft of the equivalent temperature index. So is a representation who must be explained. So what is here inside? We have a cold sensation, slightly cold sensation between the dashed blue and the black line. Between the two black lines is a neutral sensation, slightly hot sensation, and a hot sensation above the red line. And we can see here some of the parts are in the good region. The parts are the lower parts, because there we don't have ventilation. But the other parts, like scalp, chest, and so on, are showing a sensation of a little bit hot. Comparing now the values of the classical diffuser with green and with yellow lobe diffuser, we can see that the sensation of draft previously showed is present here, because the mannequin exchanged more heat with the environment in the areas of the hand. Meanwhile, we can see from the simulation, we wanted to see these zones. So we can see here the with red, and after that, because it was not possible to show in this way what is cotton, this region of the hand is cutted. So in this area, the draft rate and the velocity of the air is very high. So a lot of energy, a lot of heat is changed with the environment. Meanwhile, with the other diffusers, we can see that the region with red is not existing on the right side and on the chest of the mannequin. Now, comparing the thermal sensation vote from the mannequin, from the human subject with predicted mean vote, and with the predicted mean vote from the center, and with the predicted mean vote from the mannequin, because we find a relation to calculate from the equivalent temperature the prediction mean vote, we can see that the classical diffusers are showing a state of minus 0.05. And more than this, all the states are showing in the center, right? Because we have that the ventilation system blowing air directly to our suns. More than this, we can see that the PMV on the, because I was telling you at the beginning that we want to compare also different measurements systems, we can see that the PMV measured with this tool are showing values which are far away from the thermal sensation vote and from the values achieved with the predicted mean vote achieved with the values from the thermal mannequin. And these values are also in these tables. And more than this, we can see here is very relevant. So thermal sensation vote is the last one. With the mannequin, it's almost 0.2. Meanwhile, the PMV in the center of the car, as I explained before, is minus 0.2.5, but in the seat is minus 1.75. So these states are very, very different. In conclusion, apart that of course the numerical simulation are showing us, are helping us to understand better these phenomena inside of the vehicle environment, we can say that on one hand, some of the actual standardized indices, evaluation indexes, are not updated or up to date to be implemented in this environment. Meanwhile, our solution proposed, that means the aileron diffuser are improving the thermal environment inside the vehicle, and we hope that in the future we will implement in another project, and we are connecting. Actually, we are going on with the measurements to test more and more this kind of diffusers. Thank you for your attention.
Thank you very much. Do we have questions? Okay. Okay. First we can.
Thank you for the presentation. The diffusers in the car are used also in cooling and heating mode.
Yes.
But as I noticed, and correct me if I'm wrong, you have made the experiment only in cooling mode.
Yes.
So, what do you believe that it will be the effect of these diffusers in heating mode? Because we have more turbulence, and we are going to have more evaporative cooling from the skin, and that's your opinion.
As I know, if I'm not wrong, but I was reading before the measurements, I know that any of these kind of the diffusers, I mean the windshield from the foot, are designed for different seasons. I mean, only to cool down, we must use from those from the dashboard. If we will heat with those, we'll have a higher temperature at the upper part of the car and the lower temperature. So in this case, the thermal comfort will be not for sure achieved. And this diffuser was designed only to cool down, and the diffuser at the bottom for the fuels were designed to heat up the car during the winter. We didn't test that because we didn't thought about this.
Thank you.
Yeah, there is an important point. Could you put back the picture where you have the PMV assessment as a map inside the car?
Let's see. Can you put back the presentation, please?
Because I think there is some misinterpretation and misuse of PMV.
Misuse?
Because you cannot use really PMV inside the car. And you cannot compare apple with pear. Because, for instance, when you use the so-called fungerometer, then you have the sensor which is looking also at the back. What kind of surface of the body have you used for calculating the predict mean vote?
Predict mean vote?
Yeah.
So we was using, I think, was metabolic rate 1.
No. I mean the surface, the body surface.
But I was not. Wait.
Yeah. When you
Let's talk on the image.
Come back to the image first.
This one.
How you can map
This one.
in a point? It's a map of PMV.
Because yes, it's a map. Because we can extract.
It's not possible. Doesn't make sense.
Let
me finish the point.
Okay.
The point is, you know how has been derived the predict mean vote? Through the thermal balance of a body. That means you have an average heat transfer coefficient for convection, which is based on the height of a body, 1 meter and 60 centimeter, and so on. You don't have a person which stay inside the cell of 1 centimeter by 1 centimeter by 1 centimeter. Then it doesn't make any sense to map the predict mean vote like this. Yeah.
This is the concept of the local PMV that has been extensively used in the literature, even by Thunder himself. It is adjusted, and it is also measured in the standard for vehicles.
There are a lot of stupid things going around because still, if you go back to PMV, again, it's a whole body assessment, not piece of body. I would like to see where it's written because I don't trust this. And the second point is, sorry, let me finish. No, we can discuss later on better on that. The second point is you cannot compare the measurement with the fungerometer and with the mannequin because you have the body which is like on the seat. That means there is conduction there, which is poor because it's insulated, okay? When you put the sensor is seeing radiation, convection, and so on.
Yes.
Then this is explaining why they are so different, okay? Because you are comparing something which is completely different in these two cases, okay? And my opinion, again, coming back to the original PMV, you cannot apply in such so close environment because you are far from the hypothesis behind its derivation, okay? Then there is no really, you should start from the scratch. That means with the experiment with the people inside the car, building up a new correlation. In that case, can have some meaning. But you have to start again from the scratch. You cannot compare with the standard traditional one.
Yes, but still it is in the standard 40505 and is still used, and is a reference in many, many articles came for the review in our field.
The standard has been just reviewed. It is exactly the same as before.
Yes.
Some small change. That means that the community, the standardization community, didn't take care of what you are saying, that there is this local PMV, because it's not proved.
Yes.
It's just a theory.
Thank you.
Okay. Thank you very much, Professor. Thank you very much. And this is all for today. So thank you very much for participating, to all authors and presenters, also for chairs. So see you tomorrow. Have a lovely evening.